You got that wrong with that. That's great. That's good. For real? I told you. Dude, you put the
everybody get your, I still have 3 copies here and several homeworks here. Okay. Okay, good morning. Now, comments.
I got a question.
Okay.
Nah, taking he ain't got no question. He's taking his L.
What is it?
What if I wrote C for number 1, but I picked the wrong one? Like, no.
If it's wrong right here, it's wrong.
Yeah. He took his L. Don't worry about it.
See, I picked D for C. But
That's okay, right? You happy?
Yeah, he good.
Huh?
He good.
Any questions about the test? If you think which one is wrong, right? If you get marked, that means that is wrong, right? And there are total 55 questions. Right? The first number is the red one is the numbers you get it correct. Then you multiply by 2, that is your score. Out of 100. Right? Any questions? Need me explain? The question, I believe, is not that difficult, but there are a lot of details you need to memorize. For example, what is the symbol for voltage? What is the unit for the electric charge? Something like this. And also how to represent a number with scientific notation, engineering notation, and all these things change the unit from volt to millivolt or microvolt. All these fundamental things. So any questions want me to explain?
Are we going to go over it? Are we going to go over it sometime? I'm using the study guide, so I need to know.
Okay, let me do this. You review your test first. Check your textbook or ask your friend or anything. If you still cannot figure out what's the right solution, then let me know. Okay? Yes.
Your homework, the way you score is out of 50, right?
Yeah, the homework is each one is 10. So usually we have 5. So everything is out of 50. If we have 6, then that will be out of 60. Right? Okay?
Thought I was going to
You cannot find anything in the book. What question is not in the book?
Yeah, I'm in the 7. I'm no dude right there.
Power dissipation. Power dissipation, that means we have to calculate the power. The power equals the voltage current. That is the first thing you can. The second one, you can use the voltage squared divided by resistance. Voltage squared divided by resistance. The third formula is the current squared times resistance. Also in the slide and also in the textbook.
I'm just mad.
Any other questions?
I'm out of line for this man. He out of line. You out of line for this man.
Come on, man.
You out of line. You out of line.
I can talk.
Bro. I just, oh, bro. I didn't know how to. Also,
Oh, I didn't know.
He said it. That's all I remember. He said, no. Oh, yeah. And you know, bro, on this one, I ain't gonna lie. I almost peaked deep, but then I read them, and they all said about the same thing, and I did it.
Okay, today we are going to discuss new chapter, chapter 4, series circuit. That is the real circuit analysis. First one, all circuit, complete circuit must have 3 components. 3 attributes, not necessarily component. Right? This one is the circuit. So what do we have here? What is on the left?
A source.
This is the source. Usually voltage source, sometimes current source, but most probably is voltage source. What are R1, R2, R3?
Resistors.
These are resistors. So we call this load. So that means takes power from the source. The other thing is it's wire. So we must have closed loop. Right? So if this one, for example, is broken, then this is not a circuit. If we have a switch, that means that switch needs to be closed to have give us a closed loop. Right? So we need to have 3 attributes. First one is the source, then a load, then a closed loop. That is the circuit. What is the source? A load and a complete part. Series circuit means
This is a source, a load, and a power.
is the one that has only one current path. That means we have only one closed loop. Another word, that means the current can only flow along one complete path. Look at the first one. The current, suppose, comes out from this positive, then flow all the way back to the negative. So this gives us a closed loop. The question is, how many loops do we have here? There's only one, right? So the current goes from here, then pass R1, pass R2, pass R3, then goes back to the negative terminal. So that's only one. So this is called a series circuit. Everything here, the source, the load, are connected in series. Second one, looks like this is more complicated. Is this a series circuit?
Yes.
We just follow the rules. Let's check the current. Again, from positive, and then we pass R1 from one terminal. Oh, that is important. So you pass R1 from one terminal, then goes to the next one, then pass another terminal, then go to the next one, then to terminal 1, then to the next one, then goes back to negative. So again, there's only one closed loop, complete closed loop. This is also a series circuit. Although looks like this one is a series, this one looks like not that series, right? But it is a series circuit. How about the third one? Is this a series also?
Yes.
Yeah, it's a series. So you go from positive to this, okay, pass through this one. So there's only one current loop. So that's easy, right? So if I give you a circuit, you need to determine if it's series or not. You just follow these rules. If there is only one current loop, then that is a series circuit. Because there's only one path, so the current everywhere along the path will be the same, will be equal. Good. So we have an example here. You may already, you may need to do this in the lab for the starting maybe second one or third one. Suppose we have a source here, and this one is a current meter, ammeter here. You know how to connect an ammeter into the circuit already, right? Yeah. So the positive, because this is the DC, so we haven't discussed DC yet, but this is source. So this is positive, a negative. So the current goes into the positive terminal. Usually, what color is it in the lab?
Red.
The red, right? So the negative usually is black, right? So this one here coming into the positive, get out from the negative. What is inside is actually only a wire, right? and this one pass through this R, then pass through this, and another R load, then pass through this. So is this a series circuit?
Yes.
Yes. Right? So that means all the current flowing through the loop will be the same. Right? So we assume, we can see that the meter shows 2.0 milliampere for this current. That means the current at this point is 2.0. What is the current here? Still 2.0, right? How about this one here? Right? How about this? Okay, all these meters measure the current in a series loop. So in practice, we do not need to use all this. You need only one. Right? You can connect the meter to here, or to here, or to here, or to here. We don't need all this four. This just shows that all the currents along a series circuit will be the same. If you do like this, you can see all shows the same number. Right? I remember in the first homework, you can put the fuse in here or here. That is almost the same thing. The fuse actually detects the current. If the current is too large, then the fuse broke, right? So protect the circuit. So that is very similar to this ammeter. Okay, does this make sense? Any questions on that? All series circuit, that means, look, when you connect, this is positive and negative, then you go in from positive, go out from negative, positive, negative, you cannot switch this. Right? For some AC circuit, you can switch, right? But for DC, you cannot. Later time, we are going to discuss more details here. But so far, you only need to know it must be in series from one terminal in, from another terminal out. Right? Okay, so all the numbers displayed on the meter must be exactly the same, 2.0. Is there any possible that if you look at this, in reality, they are not the same? For example, one is 2.0, another one is 2.1. Is this possible? Another one is 1.1.
No.
No possible? I mean, in real life, you go to the lab, you connect like this. You see, okay, this meter shows 2.0, another one shows 2.1. Is this possible? Yes. Okay? It is possible. So what's the problem here?
The instrument's not properly calculated.
Okay, your accuracy, right?
Yeah.
At the very beginning, we discussed the accuracy, precision. There are a lot of things for you to read the number and also for the equipment to show this one. So maybe you need recalibrate the meter. So that's one reason. Okay? But anyway, that is possible. But theoretically, it must be the same. So if I ask you to measure like this, you can determine the error. Right? So suppose the correct one is 2.0, but this one is 2.1, so the error is like 5%. So you can calculate the error. The error is use the real one minus the theoretical one. So 2.0 minus 2, then divided by 2.0. So converted into a percentage, which equals 5%. So, okay. If we are given a series circuit as in the previous example, we have three, R1, R2, R3, three resistors connected in series. Sometimes I want to know what is the total resistance. Right? So this gives us the total resistance of resistors in a series circuit. So what do you think it should be?
Just adding up.
Add up all together, right? So it is the sum of all the individual resistors. Right? Now we have this example. What do we want to know? We are given these three numbers. Right? The first one is 680, the second one is 1.5 K, the next one is 2.2 K. What we want to know is what is the total resistance? How to calculate this one? First one, you need to determine if this circuit is series. Is this series circuit?
Yes.
Right? Series circuit, this is the source. All other three are the load. So the total resistance usually means there are different meanings, but usually in common, That means the total resistance looking from the source into the load. That means if you look at, you want to find the total resistance, you stand at this point, looking into the load, this direction. So what is the total of these three? Does it make sense? You do not look at this point, okay, or this way. So that's the total resistance in this problem. So that means the total resistance looking to the load from the source. So you just remove this source and look at all this. And we know this is a series circuit. So the total resistance will be the total of the individual resistance. So that means you add all these three together. So now we need to use the technique we learned in the previous lectures, how to add these numbers. Looks like these numbers, they have different units. This is K, this is K, this is 680. So that means you cannot directly just add these numbers, 680 plus 1.5 plus 2.8. That's not going to work. Right? What we need to do is we need to convert them into the same unit. You can convert this into K or into O. That doesn't matter. Right? So in this case, it looks like we would like to convert into K. That is better, right? Based on experience, that will be much more efficient. Right? So this one will be equals converted into K, or this one will be equal to 0.68. Right? Then plus 1.5 plus 2.2. Right? So that result equal to you can use a pencil to calculate this, or you can use a calculator. Right? But anyway, you need to get this correct. In homework solutions, somebody get incorrect adding numbers. So the result in this example equals 4.38 kilo ohms. Okay. So any problem on this one? That's easy, right? So how to do this? I'll give you a circuit. Ask you to find the total resistance. How are you going to do this? Step one.
Measure each resistance.
You just add all this resistance. A little time you're going to find out, okay, you add all this together, wrong. Step one is you need to determine if this circuit is series or not. If series, then you add all this together. That is correct. If they are not, we are going to discuss 2 lectures from today. Then that a parallel circuit, you cannot just add them together. That means 1 plus 1 not equals 2. Actually, 1 plus 1 equals half. That is for parallel circuit. So this only works for series circuit. So step one, you need to determine by yourself, is this a series circuit? Yes, then you just add all this together. Does it make sense? And then after parallel circuit, we are going to discuss a combinational circuit, series parallel combined together. So that's even more difficult. So you need to be very careful where you are. Which part is series, which part is parallel, then how are these connected? So you use different formulas to calculate, not just add all this together. But this is the first time. It's very simple. Series circuit, add up together. But you still need to determine if it is a series circuit. Yes?
Would parallel be considered as AC circuit?
For AC circuit, for DC circuit, all are the same. So that's why we didn't discuss DC, AC. So even in AC, the rules are still the same. Okay? Is everything good here? Okay. Now we have this circuit, still series circuit, right? Still the same circuit. We are given the resistance. The first one, R1 equals 680 ohm. The second one is 1.5. The next one is 2.2K. We are going to have this table. So tabulating the current, resistance, voltage, and power. All the possible quantities for each of the load. For each of R1, R2, and R3. And even the total. That is very useful practice. So in the labs, maybe you need to do this. I'll give you a circuit. I'll give you a table. you need to measure the necessary quantities, for example, voltage or something, or you are given some quantities. Then you need to fill all the blanks. With the laws we already discussed, including Ohm's law, Watt's law, and all these things. And also the typical property for series circuit. For example, the current flowing through the series circuit must be the same along the path. So use all these properties we discussed so far, then we do this, right? We know the source voltage equals 12. The R1 equals 680, the second one equals 1.5 K, the next one is 2.3 K. We only know these 4 numbers. Now we need to fill these blanks. This one gives us the current. I1 means the current flowing through I1, R1, resistor 1. I2 means the current flowing through the second resistor. I3 means the current flowing through the R3. I total, that means the current flowing through the whole series circuit. And all this here, R total here, as we already discussed, is the total resistance looking into the load from the source. And we want to know the voltage across the first resistor, across second resistor, across third resistor, and also we want to know the voltage on the source. And also we need to know the power on the 1, power on the 2, power on the 3, and the total power on the load. All these numbers we need to calculate. Which one where we want to start? Okay, we already have this one. The total resistance was already calculated from the last slide, so it's 4.38 K. So we already know this. Which one you want to find the next one? The current. So we have 4 currents to find out. Which one? Okay, let me see this. For example, if you want to find the current 1, how are you going to do it? Recall the Ohm's law. You want to find the current on the resistor 1, right? So you need to use the current equals voltage over resistance. The voltage must be the voltage across that resistor. So that means this one, you must use V1 divided by R1. Does it make sense? Yes. The current flowing through R1 needs to be calculated from the voltage across R1 divided by the resistance R1. But okay, good, we know this, but we don't know that. So you cannot calculate this current directly. You may ask, how about we calculate this first? Right? This one, Ohm's law, the voltage equals the current times resistance. We need to know this, but we don't know. So we cannot do that. We can also use Watt's law. The voltage, the power equals the voltage times current. If we know this one, then we can calculate the current. But we don't know that. So we only know this resistance. So it looks like there's no way we can directly calculate the current here first. Same thing applies to second one, third one. So there's no way we can do this. But we know this is a series circuit. It has a characteristic. That means all the current must be the same. Right? So this current equals this current equals this current. That doesn't help, but equals the total current. This one helps. That means each current equals the total current. So what is the total current? Total current equals total voltage divided by total resistance. Again, this is the Ohm's law. Alright, so we know the total voltage, 12, and total resistance, 4.38 K. So we use this one, divided by this, we get the total current here. Can you calculate? 2.739. Okay, we need only like 3, right? 3 digit, 2.73, right? What's the unit? Milliamperes, right? Because this is V, this is the ohm, so and there's a K here, so that's milli. So 2.3 something, right? Everyone get this? Everyone knows how to calculate this?
Yes.
Okay, so use voltage divided by total resistance, give us the total current. Then the next one we are going to fill all these 3 blanks. Series circuit, all the current must be the same. So you just copy this number to here, to here, to here. That's it. That's easy, right?
Yeah.
Okay, so the result will be equal to 2.74. We take only 3 significant digits. The reason is here is we have only 3. Alright. Any questions on this? Okay, no. Next one. What do we do next? We can do anything else, right? Alright. So for example, we do V1. I will ask somebody to tell me how to calculate the V1 here. From the information we already know on the left. Anyone? You want to try? We calculate this one. So multiply. So the voltage equals the current times the resistance. But you need to make sure corresponding current, corresponding resistance. For 1, you need to use the current 1 times the current resistance 1. So 2.74 times 0.68.
1.86.
1.68. Okay, so there's a milli here, which means negative 3, right? There's a K here, means positive 10 to the positive 3. These two cancel each other, give us 1. Right? So you don't need to use this negative 3, 10 to negative 3, 10 to 3. You look at this, you know, these two cancel. So you just use 2.74 times 0.68. So that is like 2/3, so it's like 1.8 something. That is correct. So 1.8 watt. What is the unit? Volt, right? So 1.8. So the result will be equal to something, okay? 1.8. How about this one? Same thing, right? But we need to use this number multiplied by this number. So we get this. And 3, we get this number times this number, we get this. How about this one? It's already 12 here. Should we double check if this one times this equals this?
Yeah.
Sure, because how we get this one? We use this one divided by this, right? So
Yeah.
these two multiplied must be equal to this. Otherwise, something wrong here. All this thing will be wrong. Right? So we calculate the current, we calculate the voltage. The last one is the power. We have 4 powers here. Power 1. The power dissipated on resistance 1. How to calculate this? Anyone? V squared over R. Okay, perfect. So this one will be equals to V squared. We already know here, right? Use this number squared, then divided by this one. Right? That is one way to do this. I want another way from somebody from here. Okay, I squared times R. So use this squared times this one. Right? That's also good. I need a third way. Anyone from here? VI. Right? So that means P equals V times I. You can try these 3 methods. Do you think the result here will be the same?
Yeah.
Yes, it must be the same. If there's something wrong, that means your calculation is wrong. So it must be the same. Come to the same result. So this is the power dissipated on the resistance one. For the homework, you calculated the last one. You calculated the power. I think you everybody did that correct. And ask you to calculate the energy. And the energy is not here. Okay, the energy you need to multiply by t, right? The time. Somebody just multiply by 2. That is not correct, right? The reason is we need to use 120. We need to use a second instead of a minute. Sure, somebody uses, okay, use hours, right? So give me the unit is watt hour. That is still good, but not the best we want. The best we want is you should give me the unit joules, right? The watt times the second. That is what we want. Sure, you can use watt hour, but that's not standard unit. Okay? What is P2? We can use still the same three formulas to calculate, but we need to use this number and this number, right? And also this number. So use any two, use one of the three formulas, you calculate here. Same thing, apply to this. Any questions so far? Before we come to the last one. Everybody is good? So I will give you a quiz, pop quiz now. Can you do it?
Yes, right.
No.
Okay. No?
No.
So what's the problem?
I just got a problem.
Oh, okay. So here is the thing. But you need to memorize the formulas. Although I said in the test you can bring a piece of paper. That's only the first time. Later on, because you want to be an electrical engineer, electrical technologist, all these things you need to put in your brain, in your head. So you cannot every time you bring a piece of paper, that is a book. There's no way to do this. Ohm's law, Watt's law, all these things you need to memorize. All this you need conversion. The properties of a series circuit, parallel circuit. You need to know this. Does this make sense? So actually for the first test, I didn't see a lot of you bring the paper. That is good. That is my purpose. Although I said you can, it's not necessary. It's pretty simple.
Didn't realize we could.
Oh, maybe they didn't realize we can. But still, that is good. Any questions? That story when I was a student, okay, so the teacher said, okay, you can bring a piece of paper or even anything. And everybody bring a lot of things. There's one guy bring nothing, only a pen. And he's the first one, he's the best. Finish the test very, very quick and get a very high score. So bring the piece of paper help a little, but not necessary. And it is actually it's bad for your future. So you need to force yourself to memorize all these formulas. You need to. Is this clear? Okay. So next time I may say no any piece of paper, only a pencil. Square paper. Yeah, next time maybe. You do. In the final, that's it. Okay. In the final, nothing. So you need to memorize everything. You put everything you want in your head.
Use the first time.
Okay, so now we have all the blanks filled except this one. Now I will ask somebody. Don't say it. I ask somebody to calculate. How are you going to fill this number? Can you tell me?
Add them all.
Add them all. Which one? All this?
All of those five.
Okay. How do you know?
I took a guess.
You took a guess. Alright. Who support this idea? Add all this all
It
together.
makes the most sense to me.
Alright.
It makes the most sense to me.
Do you know why? Make more sense. Do you know why?
It's in series, so you just add them all up.
In series circuit, so far we only said all the current must be the same. We didn't see anything else. Also, the total resistance equals the sum of the resistance. We didn't see the total power equals the sum of all the powers. You're good. You're correct. Yes. So now this is the other property. Not only for series circuit. It is for any circuit. No matter the series, the parallel or combinational. The sum of the individual power must be equal to the total power.
Got it.
Okay? That's good. Not necessary to series. So this one, we keep this one to the last because don't want to confuse you. This is not only applied to series circuit. That's what I mean. It's good. But usually we use this method to double check. I want somebody to use other ways to calculate this one. Anyone else? Let me ask you, okay?
Can't you do voltage sum, carrot sum?
You use how do you do it?
The formula,
Okay, which one formula? We have three numbers.
V squared
just
yeah,
over R.
down.
V squared over R. V squared over R. Right? So this one equals this, or you just repeat, right? Current what?
Time voltage.
Times voltage. Yes, perfect. There's another one. Don't look at your notes, right? Voltage squared over R. We mentioned. This is your first one. Right? What's the next one? What's the last one?
R squared.
Okay, current squared times R. Right? All this you do not get confused. All these three formulas, right, are equivalent. You need to use the correct one. Right? So all these numbers. So we have 4 ways to calculate this number. Okay? 3 formulas. Watt's law, right? And or you can use the property. Add all this together. It must be the same. Okay. 1.86. We are good, right? 4.11 and 6.03. Let's comment this column here. Any conclusion do you have? What is the relationship between the 3 red numbers and the black, this total number? Right? They add up together, we are equal to this, right? This is 10, 11, this is 9, this is 10. So, all equals this. And this is the next law we are going to use. Now we already know that. Maybe in the lab you need to verify that. Yes, you build a series circuit, you measure individual voltage, and you add them all together. They must be equals the voltage source. That is a theoretical result. When you really measure this, do this, the result may be not different. Maybe a little bit different. For example, this one maybe you add up together, maybe equals 11.99 or 98 or something. Okay, that is possible. That is reasonable also. Okay. This one equals 5.1 milliwatt. This one is 11.3. This one is 16.5. Okay? And we add all this together, or we calculate by other 3 methods. The result equals 32.9. Any question?
That first one, it's always going to be the same, right? Like.
Or this one? Yes, that is a property for series circuit.
Okay.
This is only for series circuit.
Okay.
I don't want to discuss more until next time. I can't try to confuse you. So this is only for series circuit. All this must be the same. We mentioned all the current will be the same. In parallel circuit, this is not true. This one cannot be the same. You cannot just say, okay, I get this one, then put all this the same. That's not going to work for parallel circuit. Yes.
So, I mean, it won't always be the same, but in this case, is the reason we got milliwatts.
The milliwatt. Okay, good question here. What is this milliwatt? My suggestion is that you use all standard unit to calculate this one, then you convert into a proper unit. For example, if you want to use the voltage times current, you use the 1.86 times 2.74. This one is V, this one is MA. So multiply together, that will be MVA, right? V times A give us the watt. So that's why it's called M watt here. Does this make sense?
Yeah,
later time you are going to familiar with what I said. If you still don't like this, you can just use 2.74 times 10 to the 3, negative 3. That is this M, right? Then that means you converted this one into 8. Then you multiply 1.86. What you get will be 5.1 times 10 to the negative 3 watt. Then that's 10 to the negative 3 will means milli. So you still convert this one. Does it make sense? Alright. In this, if you want to use the voltage squared over R, so voltage squared here, 1.86 squared over this one. So we know V squared over ohm, that gives us watt. But there's a K on the bottom, on the denominator. So that K equals 10 to the 3. So bring out, that will be 10 to the negative 3 still. Means this minute. That's really good question. So has a very practical usage. So you can easily see, for example, this one times this. If you want this one times this is M, 10 to the negative 3. This is a K, 10 to the 3. They multiply together, give you just the V. Okay, any further questions? Everything good? Okay, very good. Next. In the example before we discussed in the flashlight, usually we have like maybe we have only one battery, 186. What's that? 18625 or something. Anyway, sometimes we have more than one batteries. How do you connect these batteries? Negative, parallel, series.
Series.
For example, in the car battery, the output voltage equals 12, right? Usually, as far as I know. But each cell is only 2. We know that from previous, the chemical battery, that is only 2. So how to get 12 from that 2? We need to know how to connect batteries or connect voltage source. So here, voltage source is in series. One way to connect is in series, which means we have other ways. You can connect in parallel, you can connect in combinational, like the Tesla's electric car. What do they have? What do they have? Just battery, right? That's the most important part. The battery is a lot. They cannot build only one cell battery for this big one. They need to connect. So how do they connect these batteries? One simplest way is a series. For example, here we have one battery here, which is 9 volt. This negative, this is positive. And this one is negative, positive, negative, positive. I connect like this, as you said, negative to positive. This is called connected in series, or series connection. So the total source, the negative is here, the positive is on the very top. This is a series connection. Any question? Okay, now question is, what is the new voltage of this combination? This is series 27. The rule is we just add all this together. You can think like this one. This is the first floor, 9 feet, suppose. Second floor, another 9 feet. Third floor, another 9 feet. Now we want to measure the total height from the bottom to the top. So you just add everything together. So 9 plus 9 plus 9 equals 27. Does it make sense? That's easier to memorize, right? So the result will be equals to 27. Right? 9 plus 9 plus 9 equals 27. Any questions?
And that's in series.
That is in series. In series means there's only one current path. See, you can see. If you trace the current, you have only one current path. You do not have two.
So when you do it in parallel, your voltage won't change, but your
In parallel. Okay, don't want to confuse you with parallel right now.
Okay.
Parallel, So we are going to discuss next time. But parallel that means you have at least the 2 paths. In this case, if I go from the top, I have only 1 path, so that is series. Parallel means you have at least 2, 1 and 1. Any question on that? So we add all these sources together, we get the total source for series connection. Is what I just said correct or not?
I don't think it's correct.
You don't think it's correct?
No.
Why? Give me one example that is not correct.
Okay, I'm probably completely confused with what I'm in this fast to learn, but like in a case where you're running it like this, I believe only your capacity increases and your voltage remains the same because it's in series. So if they're all connected like that line there, then the voltage is going to remain a 9-volt source out on the ends, but your capacity of how much you can use of that's going to increase. Is that correct, or am I crazy?
You mean connect again in parallel?
No. Like literally in series. Like if you take a battery post, you take the negative on this side, you hook it into your car, and then you connect the hot to the negative of the other battery, and then daily change just like that, and then you take the last one and you connect it to your car. Then you get more capacity, but you still stay as a
The same 12-volt
source.
Okay, so that is in parallel connection.
No, that's parallel.
Yeah. If you positive connect to positive, negative connect to negative, that is a parallel.
Okay. So looking at the picture, that's what I'm thinking is that it, because the picture looks like parallel, but it's not, is what's throwing me off.
You mean this one?
Yeah, look at that little picture there, because isn't that what that's doing? No, not there, on the,
At the very beginning. You mean this one?
no, the one you were just on, where it's just a line.
Yeah,
That looks like,
two.
because for it to be parallel, that's got to be more than one line there, right?
More than, if it's parallel, must be more than 2 branches, means 2 loops. For example, the current, you go somewhere, you need to have, okay, I can go this way or I can go this way.
Right.
So in this case, you trace the current, you can only go, right? You can only go, if you trace the current can only go here, then go this way, There's no way you can have, okay, up to this point, oh, I may go this way or I go this way. So you have only one option. So that's only one loop.
Yeah.
So this is a series connection.
Okay.
Right? So my question is, if you connect any source like this in series, the total source, the total voltage will be equal to the sum of all this, the individual. So in this case, 9 plus 9 plus 9 equals 27. My question is this always true? If you connect the batteries in series, then you always add all this together. That is my question. Right? Not necessary. Even you connect in series, but if the polarities are switched, most probably that is wrong. Right? You do not make any sense to do like that. But sometimes that just by mistake. Like in this case, positive, negative, negative, positive, negative. Right? First, let me ask: is this still a series circuit?
Yes.
No. Yes. No.
Yes.
See, look, the current coming in all the way. That's only one loop. So this is still series connection. But compared to the last one, in the last one is positive, negative, positive, negative, positive, negative. So here is a positive, negative, negative, positive, positive, negative. So that means the polarity of this one is switched. You change, right? You reverse.
You switched it on.
Right? So supposed to be positive is on the top, negative is on the bottom for this one. But now you reverse this one. So what happened to this? So what is the total source for this connection?
9 volts.
9 volts. How you get 9 volts?
You reverse the polarity, it becomes a negative voltage source.
Okay, so this one I still use 9, but this one will be a negative 9.
Negative.
Right? So use 9 minus 9, then plus this one. This is positive 9. So not necessarily you directly add all these numbers. Okay, still 999, add up together 27. No, you need to consider the polarities. Does it make sense? Right? So for example, if you have the flashlight, suppose it takes 2 batteries, right? So sometimes you just put in 2 batteries, you turn on, nothing happened. What happened? Because you connect like this. That means 1.5 minus 1.5 equal to 0. That means you connect to nothing. The source is still equal to 0.
That is tight. That is tight.
Does this make sense? Alright, so you need to connect in the right way. Question?
No.
Alright. I don't know any reason why somebody will connect like this, except this is a mistake. As you said, you can connect 2 batteries in parallel, although the voltage is still the same, but they, as you said, increase the capacity, give you more current. That is good, we have a reason for that. But for this one, there's no way, except this is a mistake. So don't connect like this.
Okay, so what crazy after?
Or maybe there's a fine reason to connect like this. Anyone can explain? For example, if you have a flashlight, it's very long inside, right? But the light bulb only takes, for example, 9 volts. But you need to put the 3 together, otherwise you cannot form a closed loop. You have 3 batteries, each one is 9. How are you going to connect inside? Does this make sense still? So the flashlight is this long, Each battery is this long. So you need to put 3 inside so to form a closed loop. Remember the circuit we discussed at the very beginning? This closed loop, right? You need to put these batteries, 3 batteries inside to have a closed loop. Each one is 9, but the light bulb you change takes only 9. If you connect like at the beginning, the first one, you get a total of 27. You are going to blow the light bulb.
Okay.
Make sense? So the only way you can connect is like this. So these 2 cancel each other, but still give us a closed loop. So that's the only reason I can think you connect like this. Does it make sense? Okay. This is for engineering. So there's no theoretical use for this connection. It has a practice. Okay. So the result for this one is 9. Next one we are going to discuss Kirchhoff's voltage law. That is another one of the most important laws. Kirchhoff's voltage law, that means there's Kirchhoff's current law, which will be discussed for parallel circuit. But in this case, Kirchhoff's voltage law. Kirchhoff's voltage law applies to a series circuit. Remember, in a series circuit, what is the relationship between all the current? They must be the same. How about what's the relationship between all the voltages? We already know that from the table. You said V1 plus V2 plus V3 equals the source. That is Kirchhoff's voltage law. All the voltages along a loop add up together must be equal to the source voltage. So the sum of all the voltage drops around a single closed part of a circuit, which this part is a series, is equal to the total source voltage in that closed part. KVL applies to all circuit, but you must apply it to only one closed part. So that means the circuit you apply it to must be series. Must be closed loop. So in series circuit, there's only one, so we can use that. A mathematical shorthand formula for this is the sum of all the voltage equal to 0. Anyone? Everybody familiar with this represent notation, right? No? Okay, so let me explain. So this is summation called sigma. Means add all these VI's. This is a subscript, not current here. We can use this chain to K to M to anything. This is just a notation. So I, what is I? I means from 1 all the way to n. Both n here is an integer. For example, n equals, in our example, n equals to 3. That means I equals 1 when I equals 1. So that is V1. When I equals 2, give us a V2. When I equals 3, give us V3. V1, V2, V3 are okay, obvious. See? V1, V2, V3. All these 1, 2, 3 are subscript. Does this make sense? So that I is called a subscript. Means 1, 2, 3, can be 4, can be 5, can be anything. So I from 1 to 10, that means you V1, V2, V3, all the way to V10. The sigma before that means you add all these together. Right? So this formula here means V1 plus V2 plus V3 plus V4 plus I don't know how many all the way to V sub n, right? Does it make sense? So this formula here, okay, on the left means V1 plus, because this is the sum, right? Plus V2 I equals from 1 to n. So V2 plus V3 plus maybe V4, maybe V5, all the way to V sub n.
So
This-
whatever amount of voltage is down in the circuit is plus all of those.
We are discussing the notation, the meaning for this one. But this one applies to circuit, yes, that is the case. KVL means all the voltage add up together equals 0. But first of all, you need to know what's the meaning of this. Does this make sense?
Yeah.
All right, let me give you a quiz, right? Sigma I equals 1 to 3 equals what? Let me write this. Sigma here is only I. Know this way, just only I. I equals 1 to 3 equals what? 6.
Okay. Okay. The 1 plus 1 plus 3.
Everybody agree?
What he said.
Say it again.
See this again, okay?
It's 1 plus 2 plus 3.
Because we are going to use this a lot in later following classes. For example, 110, 111, you are going to use this notation. Not even on circuit analysis. Other courses we are going to use this also. Right? Let me write. I don't have one. No marking. Anyone has a marker? I can borrow a little bit. Thanks.
Thank you, thanks as a marker.
Yeah.
So like this, sigma, right? Perfect mark, right? I equals 1 to 3. What is this? That is my question. We need to write this, decompose this right into the meaning. So when I equals 1, what is this one? So that is only 1. Then when I equals 2, so this is 2. When I equals 3, this is 3. That's all. We have only I equals 1, 2, 3. So that's only this one.
Where did you get the 2 from?
2 is from 1 to 3, that means you need to have a 2.
Oh, so you have to add the 1 to equal.
This one means from 1 to 3, not only 1 and 3.
So if the one at the top was 4, I would have to put 3.
Yes.
Okay, I got it.
Alright? Now, this sigma means summation, means add all together, so you need to use add, like this one. So that's why you get 6. Does it make sense? Alright? So I'll give you another one. I'll change this one to 10. So that means equals 1 plus 2 plus 3. Do we have 3?
Yeah.
Yes. Do we have 4?
Yes.
5?
Yeah.
And 6?
Yeah.
I don't want to write all this.
all
You just write this all the way. Which one is the last one?
10.
10.
It's 55.
55. Okay?
I got it.
Does it make sense?
Yes.
Okay. Everybody are familiar with this thing, right? Okay, I'll give you an extra, right? So another. So sometimes you use this one. Huh?
Oh, what is that?
This is sigma means add. This one means multiply.
Okay.
The same thing, right? Just the different notation. So for example, I from 1 to 10, I that means still 1, 2, 3, 4, all the way
multiply.
to 10. But instead of summation here, we need to use multiply. Okay? So that is another. But we won't use this one in our class. So if you study math later time, you need to take math class. Right? K1, K2. Later time, you are going to use this one. Okay? If you don't want, you don't need to know this. But you need to know this one. Okay, any further question on this? You look at here, all the voltage sources add up together equal to 0. Everybody understand this? Is this correct? Yeah?
Only if 10 is 0.
Do you think this one in the box is correct? No. Who says not correct?
No.
Why is it not correct? It is correct. Look at this again.
Oh man, this is one of them times.
Look at this compared to the theoretical work.
Drops around.
You don't have any objection?
There is no
You just
vote.
totally agree with what here?
There's no vote.
Huh?
Is M 0? M 0, then yeah, that's right.
No, n equals, in our example, equals 3. Because we have V1, V2, V3.
Oh, no, it's wrong.
So it's wrong.
If n equals 3, then it's wrong.
So how are you going to check why it's wrong?
It doesn't equal 0.
Because it should equal 6 if it's a 3.
No, this one, V1 means the voltage in our table. Remember that? V1 plus V2 plus V3. Obviously, in our example, this n equals 3 because we have only 3 resistors. So it says V1 plus V2 plus V3
So it'd be V6.
equals, okay, V1 plus V2 plus V3 not equal to V6.
Oh, it's not?
That means the voltage or this V1 plus V2 plus V3 add up together. You cannot add the subscript. It's not equal to V6.
It just equals 6 by itself.
No, that 6 is my example. This is VI, V1. We already know the voltage. We calculated in the table. Remember that? V1 equals, what is to 1.86 volt, right? Okay, let's come back to here. See, look at this. This one is V1. This one is V2. This one is V3.
Okay, so whatever it is,
So V1 plus V2 plus V3 equals 0. And everybody agree with this?
No.
No. Okay, so now you see this one, there's something wrong here, right?
Yeah, it should be 12.
Should be 12. So what is that 12? We give it a notation. In our example, it is
Sigma.
look at here. The sum of all the voltage
It
drops.
should be VS.
This part.
I'm on it, bro.
Right? That is
I'm on it,
VS.
bro. I'm telling y'all. It's the little thing.
Look at that, right? It says the sum of all the voltage drops. Right? This is the sum of all the voltage drops. Right? Equals the total source voltage in the closed loop. In our example, must be 12, which is in general VS.
Let's go. Let's go. Oh
So
my God.
it's 0, yeah.
Nah,
Does this make
like,
sense?
You gotta think about it, cause like when you looked at the little thing, it says V1, V2, V3, and they all got numbers by it.
Yeah.
And then you go all the way to the bottom, it's VS. You add all them together, that's what you get. So it's VS, the sum.
Yeah, the source or the sum of the.
It says, you see, equals the
Got it.
total source.
Yeah.
In our example, there's only one source. So there's VS. So this one must be VS. So this is wrong, right?
But
Yeah.
that's wrong.
No one agree this is correct? Even a little bit? Somebody?
That's for electron flow.
That's for electron flow? No, that is for the sum of voltage.
When you follow the electron
No.
flow, you get negative.
The I equals 1, so it would be V equals 1.86.
Yeah.
That's what it would be.
This I equals 1 means V1. We add V1, not we add 1.
Yeah.
Does this make sense? Okay, so here, this is the terms that we need to add up together. We do not add this I. Maybe, okay, so I give you this example. Maybe you are confused a little bit. Okay, you think, okay, just 1 to all these add together. That's not correct. For example, like this one. I equals 0 to 4 xi. I add this. How are we going to write out this one?
X1, X2, X3,
Alright, we start from 0.
X0.
So that will be x0, then plus x1 plus x2 plus x3, then plus x4.
And then it's going to be X equals X.
Make sense?
Yeah.
Is this one equals x10?
No.
No, you can't add.
We don't even know this one, right? So this one, for example, if x1 equals 5, this one can be equals -5, this one can be equals 2, 3, this one can be equals 2, this one can be equals 100.
And
Right?
because
This is just a variable.
X equals X.
Then you add this together. This is just a notation. You cannot add all the subscript together.
Gotcha.
We need to add this variable here. This variable is called x0. Okay, now this one means V1 plus V2 plus V3. That's all. To the left, right? Must be equal to VF. So that is the correct V. At least representing those, the red words. So that is control of the current flow. But that is only one way to see this. That is definitely correct. But I don't like this one. I don't like this, you write VF. Instead, I like this 0. So this slide is from the author. So this 0 here, there's a reason. Maybe he jumped too much. So this 0, I would say this is correct. But not correct as that.
Yeah, I see what you're saying.
So the control for the voltage law, in my word, is all the voltages add up together must be equal to 0. I don't like that equals voltage source. Why? Because later time you're going to see, we use a high level circuit analysis, you're going to use this method. We don't like that data because this one is not uniform treatment. We want all the voltages add up together equal to 0. What does that mean? That means, for example, if you start from the first floor, you walk this floor, climb another floor, no matter what, how many floors, where you walk, then you go back to your original place. Your total height must be equal to
Your
0.
displacement is 0.
The displacement must be equal to 0. That is what it is. Look at here, the circuit. Look at this circuit. If you start from this point, you go up to here, that means your voltage will increase by 12, right? Just like you climb the stairs, you go up by 12 feet here. Then you go down here, we know the current flows from this way to this way, so the voltage will drop. Does it make sense? So this voltage here, something like you go downstairs, go this way. Then you go downstairs again, and you go downstairs again. Then once you come to this point, your starting point, your displacement, your height change will be equal to 0. Does it make sense? So that means in my word, or with this big 0 here, this voltage plus this voltage plus this voltage plus this voltage equal to 0. That is that formula means. But unfortunately, the formula didn't treat well with the I. You forget the S. So that means S is one of the I's. What does that mean? That means in our example, the I supposed to equals 4. So I1, so V1 plus V2 plus V3 plus V4 equal to 0. Which one is V4? V4 is this guy. V4 is a negative Vs. Make sense even a little? So an easier way to memorize the Kirchhoff's voltage law is you start from anywhere, you go around the closed loop, you add all the voltage together, you get 0. Alright, so look at this one. We start from here, we go up, so what we have here is negative 12. And because this is 0, this one is 12, so 0 minus 12, so this one is 12, negative 12. And this one we know is 1.86. So negative 12 plus 1.86, this one, what is this? This is 4.11, and this one equals 6.03. You do all this, add this 4 together, that equals 0. Make sense? It's good?
Yeah.
All right. Okay, they use this example to discuss. This concept is important, right? So I will give you another example to make sure we understand this. Okay. Suppose this voltage equals 10, and I have a resistance here, resistance here. This one equals 2 k ohm. This one equals 8 k ohm. I want you to write the Kirchhoff's voltage law for this circuit. So this is R1 equals this is R2 equals this.
Yeah.
This voltage source here equals 10. This one is positive. This is negative. And this one R1 equals 2K. This R2 equals 8K. And we have a series circuit here. What I want is give me the Kirchhoff's voltage law, the formula. First one, you need to determine what the voltage on each of these resistor, right? So how to calculate the voltage on here and here?
Find the current.
We need to find the current, right? So this look like the field of the table we discussed before, right? So what is the total current? Right? We want to know the total current. Before that, we need to know the total resistance.
So we look
So
for R3.
R total,
I mean RT.
RT equals 10. Right? Here is how you write your homework or your test. You need to give me the formulas, not just give me 10. I don't know how you get this. Where did you get it? Right?
RT equals 2.
What I want
Okay.
is says R1 plus R2.
Yeah.
Good? Then equals plug into numbers. 2 plus, because both units are K ohm, so I don't need to write the unit. So I just 8 equals 10 K ohm.
And then RT equals 10K.
Does that make sense? So you need to write like this. Only give me 10. For this one, I can see. Others, so maybe not that straightforward. You don't do like that. Okay, the next one is the I current. That one will be equals use V over R. In our example, will be RT. This one will be, okay, we write this one VS here. Equals, so we use VS over RT. So this one will be equals plug into numbers 10 over 10. You write 10K. Better, right? Otherwise, this somebody may think this is standard unit. So this one will be equals 1 M8. Right? It's good. Now I need to find V1.
2 volt.
Yes. How to get that? V1 equals R
2K ohm.
times R1.
I can't see.
Right? So R times R1. So that one equals 1 M1 times 10. So that, sorry, not 10. Okay, R1 equals 2. So times 2. Equals just 2. Why? Because there's MA here, there's K ohm here, so this cancel each other. So if you want, you can write this one. 1 MA times 2K ohm, so that one equals 2 volt. Right? It's good? Right? The next one, V2 equals I times R2, so equals 1 times 8, so equals 8. It's good?
Yeah.
Alright, so now we have everything before we write out the Kirchhoff's voltage law. Okay, Kirchhoff's voltage law, we need to write a starting point. A good way is you always use clockwise. Right? There's a reason for this. Later time, again, is circuit analysis. You need to choose a direction. So you can use anti-clockwise, but better is not better way. Right? So you always use follow one way. So we prefer use clockwise. And where to start? You can start from here, anywhere. But for example, I start from here. You are from the left bottom corner. Right? So the first one. The first voltage is here, right? So all the voltage add up together equal to equals what? All the voltages add up together equals what?
Yes.
Equal to 0, right? No VS anymore. I said I like that 0.
Yes.
Does it make sense? Right? So equal to 0. I put this one 0 here already. Right? So the first one is this one. You use the starting point minus the ending point. So this is negative, this is a positive. So this is a negative 0 minus 10. So that one will be negative 10. and this one plus
2 plus 8.
this one. The current flows from here to here. So this one, the potential here is higher than this one. So we use this one minus this, we are going to get a positive number, right? So that one will be positive 2. Right? Then add another one. Again, the current goes this way. So this one will be a negative 2, positive 8. So this one here. So that one, yeah, that is KVL. Exactly correct. This is just for verify. Right? So that one is good. That is just for verification. The real is supposed to be Vs plus V1 plus V2 equal to 0. That is what I want. So negatively add. Why we put this way? Negatively. Does that make sense?
Yeah.
Let me change. We still have a minute. We change this one. Like this. But we still use this way, right? Can you? Nothing changed except this polarity. This side is positive, this is negative.
Yeah.
Okay, the original is negative 10 plus 2 plus 8 equal to 0. That is correct. This is the previous one. Now, for this one, can you tell me
10 minus
10? Why it is 10? Because we start from here, right?
Negative,
Go up,
negative
it's a
makes
positive 10 minus 0. So 10
minus 2
minus 2
Minus 8.
minus 8. So still equal to 0. Right? If I write like this one here, it will be Vs
Minus
minus V1 minus V2 equal to 0. Same thing, right? So follow the right practice, okay? Always clockwise start from this point. You may argue, how about I start from here? Okay, yeah, that's still good, but sometimes you are going to confuse and you are going to make a mistake. So this way, you always use this method to make less mistakes, right? Okay, thank you, that's it. Still have some homeworks and midterms. Please take them back, right? Yeah, you keep that.